So last week we introduced the development of the discrete choice model and the multinomial logic model that we specifically applied for the trip distribution. And we showed the method to do the calibration about the model. In the future, for the more complicated situation, like with a lot of variables, more than 2 variables, you need to rely on some statistical softwares to get the result. But for the I hope that for the if you are working on with 2 variables, you will have the idea about how to do the calibration. And in this lecture, we will continue the topic about discrete choice modeling. But instead of introducing the model development and calibration, we're gonna try to explore more features about the how to aggregate the multinomial logic model to a sample or to a population. Again, in this lecture, there will be a lot of derivations. You might, if you have already checked the slides, you will see this kind of how the conclusion is derived. So in this class, I will not go through the details about derivation. It's just about some math work. So you can try to check the details by yourself after class. I'll just give you some introduction about the basic ideas about how we're going to understand this model and at what kind of scenarios we can use this model and what's the limitations of this model. So first of all, we have a multinomial logic model to show what's the probability for to choose one mode or choose one options from the group of the alternatives, and the equation on top shows the probability of choosing the mode I. So it's determined by it's estimated by the deterministic component, which is something we have to estimate. In this model, we assume that all the individuals are utility maximizer. They are trying to maximize the utility they can get, and also we see that utility is not a deterministic variable. Instead, it consists of 2 components. One is the deterministic component that is related to some attributes of the alternatives or the features of the individuals, and also it has the random components. And we assume that the random component follows the Gumbel distribution, and all the random components are identical independent Gumbel distribution with the parameters of 0 and 1, the standard Gumbel distribution. And also the deterministic component, we assume that is a linear function of a set of utilities, or a set of the variables. So that's the all the assumptions we have for the multinomial logic model, and we have already proposed the method to do the estimation of the parameters. That's the calibration method we learned in the last lecture. And now the next thing we have to think about is what's the aggregation features. What's the elasticity of the probability with respect to the variables that we apply to estimate the deterministic component. And also we want to explore the independence from the irrelevant alternatives properties, and also the extensions to some more complicated situations, actually the development of the nested structures. So let's first go to explore the aggregation. For the here we want to understand what's the elasticity of the model, which means that what's the how the probability of choosing one mode will be modified if the some variables attributes is changed. For example, if we increase the ticket price of the train, what kind of probability modification about for one commuter to switch their mode from train to bus to car and so on. So that will be the one feature for us to understand the what's the reliability of the model we develop for that city or for that region, and what kind of disturbance may cause to the mode choice or the trip distribution in that area. So investigate the elasticity, we will first go to check the definitions of the elasticity. This is one we learned at the beginning of this class. The elasticity defined as the ratio of the changes about the demand with respect to the ratio of the changes about the price. So yi here is the demand and pj is the price for one specific product. And if in this case, if I equal to j, I and j are the same, we call them as the direct elasticity. If they are different, we define them as the cross elasticity. So that's our definition about the elasticity. This is quite straightforward. And we also know that for the to determine the value of y, there are a set of the variables about the set of the price, and we say that assume that there are j different price. So with that, we can find out a bunch of the direct and cross elasticities. In addition, if the change is very small, too small, then we can use the partial derivative to represent the smaller change about delta y and delta pj. And now let's go to see some abbreviations, like define some abbreviations so that we can use them for the future analysis of the elasticity for the discrete choice model. Assuming here we use the a variable enjkl to represent the elasticity of the probability for the specific individual n to choose the alternative k with respect to the change in the attribute j of the alternative L. So this is a general case. If we recall the definitions of the elasticity, we can write them as the changes of the probability for the individual n to choose the mode k divided by the probability of n to choose the mode k divided by the ratio of the changes in the attribute JL and the specific value of xjln for that individual. So this is the definition about the elasticity, and here xjlk represents the j's variable applied to specify the utility of the alternative L to the individual n. So there are three index here, so you have to be very careful about the one that we choose. So that one represents the j's variable in the linear equation with respect to the estimation of the alternative L, and that's the variable for the individual n. And in our previous model, we assume that the for the deterministic utility is the function of a set of the variables x1, x2, xl until you get to xj, and for each one of them, we have the p different attributes. So x0l, x1l, x2l until you get xpl. Then you can actually for the first one, it usually be set as the constant term. It will be 1 for some mode and be 0 for the other type of the mode. This one we discussed in the previous lecture. And now we can then have the more simplification about the elasticity we defined for the discrete choice model, which will becomes the partial probability of the k over partial xjl times the xjl divided by the probability of k. So this is the definition of the elasticity. And as we have already know the expression of the probability to choose the mode k, then we can further expand this equation and try to find out what's the exact expression for the elasticity. So here we will have a very complicated mathematical derivation, but it starts from the multinomial logic model. We know that for the probability of k, that will be the exponential of vk, that's the deterministic component of the utility, divided by the summation of the exponential vl for all the mode. And we can apply a slightly derivation, a slightly modification about the components on top and the bottom of this probability, and expand this one, apply this one to calculate the first order partial derivative for the specific variable xjl. And well, I will try to skip all the derivations. It's quite complicated. You can try to, in the after class, you can go to check the animation mode. With that, you will see how the result is derived step by step. Well, in the derivation, you have to pay attention about the changes of the index. Here, we do some slightly modification of the index to make sure that you will not be confused. Well, you will not be confused about some of the same index in the in this very complicated equation. And now with this kind of derivation, if we do some expansion and apply some simplification, eventually you can find out a very simple, even though you see this kind of derivation is very complicated, but eventually we'll get a relatively simple equation. So for the elasticity, with respect to the for the mode I with respect to the for the alternative k with respect to the variable j, you can find out the expression looks like this. This would be the xjl, which would be the specific variable for the individual n, times the summation of the probability for all the modes that are available. And then you have two components in the brackets, the partial vk divided by partial xjl minus partial vq divided by partial xjl. So this actually applies for the general case if we don't know the expressions of the deterministic utility. But as we know that in our previous analysis, we assume that the utility can be a linear function. So with that, we can make some further simplification. So before we go to that, let's go to see some special case. So this is the one we derived from the previous page. And we have the variables. We have p different variables for each alternative. And also, here we assume that for the deterministic component, with respect to the mode L, it's only determined by the attributes related to the mode L. So that is only the XL, which means that X1, X2, and Xj will not be applied for you to estimate the VL. So the example is like for example, for you to take the mode of the to choose the mode of the bus and train. If you choose the train, your utility may only be related to the price, the ticket price of the train. If you choose the bus, your utility is only determined by the bus ticket price. So it's not related to the train ticket price. So that's the meanings of this. What's the meanings of this assumption. And with that we can simplify the equation. So if k is not equal to L, then the component partial vk divided by partial xjl will be 0. Only when k equal to L, we can see that we can get we will have the value. So under these conditions, if k, we will get the result as for the For this component, for this elasticity, if k is not equal to L, the result is the partial XJL times the probability of L times the partial VL divided by partial XJL. So this is the kind of the simplified equation for the elasticity. But still, we can make a more simplification by assuming that V as a linear function of x. So this is a linear function. So with the linear assumption, let's see what we can get. So so here's another expansion. I forgot to mention that. Here's another expansion about what's the direct elasticity and the cross elasticity. I'll introduce this one first before I go to the linear for linear equation. So for the direct elasticity means that k equal to L, and with that you can do some expansion, and the result will be further simplified as this equation. So the one that we get from the previous slides is the cross elasticity, and here is the direct elasticity. And we can also put them together to write in the general format. If k equal to L, this is the general format. If k equal to L, that will be 1. If it's not, then that will be 0. So this is the general format for the elasticity with respect to the multinomial logic model. Okay, so that's the overall general expression about that. And now let's consider the very special case with the linear expression for the deterministic component. Based on what we have already derived, assuming that VL is the linear function of the attributes or the variable x, and we can write VL as theta 0 plus theta 1 x1L plus theta x theta 2 x2L until you get theta p xpl. And with this assumption, this component in the elasticity will be easy for us to derive. So for the linear equation, we get a partial VL divided by partial xjl as a theta j. And then you apply theta j to the elasticity. You get the very simple equation for the elasticity, ENJKL. So that is xjl times theta j times delta KL minus probability of L. So that's what we derived for the elasticity. This one is actually applied for the individual n. So you can see the index n in the equation. So it's only applied for the individual n, but sometimes the changes for this discrete model, the changes of the attributes may affect all the individuals in the city. For example, if we change the increase the price of the train ticket or the subway ticket, it actually applies to all the individuals in the city. So with that, we want to see what's the aggregate elasticity, which means that what's the overall probability or the flow changes or the trip changes with respect to the changes of the variables or the changes of the, say that the train ticket price. So with that, we want to start with one restriction. So first of all, we assume that the for some attributes, the changes of the attributes will be the same to all the individuals. So we will have this assumption: delta xjln divided by xjln will be the same to xjl divided by xjl. So regardless of the individual n, so that will be all the same. And then we can define the aggregate elasticity. So the only difference between the aggregate and the individual elasticity. Like for the individual, we have X NJ KL. So that's what we get for the individual. But here we derive the aggregate, where we will try to see what's the changes to the whole population. And to do that, we assume that the population for the mode, or the person who used the mode K is N is NK, and the potential change is delta NK. And now the EJKL will equal to delta NK divided NK divided by XJL divided by XJL. So that's the that's what we define for the aggregate elasticity. And here NK is the expected number of the individual to choose the alternative K, and EJKL is the elasticity for the number of the individuals who choose the alternative K with respect to the changes of the attributes, the J's attributes of the alternative L. And now let's do some derivations to find out what's the how we can get the formula to estimate the EJKL. Again, like I say that the derivation is very complicated, so I will try to skip most of the part, just to leave some of the important assumption. So first of all, for the value of NK, which will be the number of the individuals who are going to use the alternative K, it could be the summation of all the probability for the all the individuals to use the alternative K. Like for individual 1, it's 0.1, for individual 2, it's 0.5, for individual 3, it's 0.4. Then sum them together, that will be the expected number of the trips that will be taken by these 3 individuals. Like I'll just say that 1, 2, and 3. 1 is 0.1, 2 is 0.5, and 0.4. If we add them together, that will be 1. So the expected number of the trips for these 3 from these 3 individuals will be 1. And you can also calculate the expected number of the trips for the other individuals. And now for delta NK, that will just be the changes for each probability. The summation for the changes of each individual with respect to the alternative K. And with this assumption, with this definition, we can then do the calculation of the aggregate elasticity. So now we have the expressions of probability of K, and we know the relationship between the deterministic component and the attributes. Try to make some simplification. I will just try to skip those steps, and eventually we can find out a very simple relationship between the aggregate elasticity and the individual elasticity. So by doing that, the equation that we can get is like for the aggregate elasticity, it's just be the weighted. It's the weighted elasticity of the individual. It's a weighted elasticity. And the weight is the probability of the alternative K for each individual. So that's what we get for the aggregate elasticity. Once you have the elasticity of the each individual and you get the probability for that individual to choose the mode, each mode, then you can get the aggregate elasticity. So that's what we get, and with that we can conclude the aggregation. So we can find out equations to calculate the elasticity, especially for the both individuals and the whole population. The third point we want to address is the independence from the irrelevant alternative properties. That's actually the one we assumed for the multinomial logic model. We have to assume that the modes will be independent to each other, and if they are not independent to each other, we cannot apply the discrete choice model directly. Instead, we have to consider some extensions of that model or a different method like the probability model. So let's go to see the more details about the IAA property. So here let's start with the multinomial logic model. We assume that the probability for to choose the alternative I is determined by the utility of each mode. And if we are trying to find out the making a comparison about two different modes, say that the probability, they find out the ratio of the probability I with respect to the probability K, you can get that the that one equals to exponential Vi divided by exponential Vk. So that is exponential Vi minus Vk. So here we can see that this kind of ratio is actually independent of the any other alternatives. It's only related to these two alternatives, I and K. Which means that the other alternatives will not affect what's the ratio, what's the relative probability for the two different modes. But if you cite this one, if you apply this multinomial logic model inappropriately for some problems, for example, for the a typical example about the red bus and blue bus problem. Assuming that we have, well, at the beginning we developed two modes. One is that would be the car and bus for people who travel in the city. So for all the people who travel inside the city A, they have two modes. Either take the car or take the bus. And we assume that the deterministic utility of the car and bus will almost be the same, or we assume that they are the same. Both of them will be V. Then we can easily calculate what's the probability of choosing the car or bus, right? So from the multinomial logic model, we can calculate the probability of choosing the bus and the car. For the car, that would be the exponential of the car divided by exponential car plus exponential bus. So that one, you get the value as 1/2, and that's the probability of car. Similarly, you can get the probability of the bus. And now, I'm gonna give you the city transit center will try to decide to repaint the bus. So we paint half of the bus as blue and half of the bus as red. And with that, we have for all the people in the city, they will have 3 different type of the mode they can take. One is car, one is red bus, the other one is blue bus. And now I have one question for the whole class. What do you think about the probability of choosing each one of them? Do you think the probability of choosing one of them will be different? The probability of choosing a car will be different, or they will still be the same? So just based on your common sense, if the city choose the bus or choose to repaint the bus, half of them to be blue, half of them to be red, will you change your decision to take the bus or drive by yourself? If you have already have some decisions about that, will you decide to make any change about it or not? Anyone has any ideas about it?
I think the probability of choosing car should also be half of one. So
you below that it will be the same, right?
yeah, I
Okay.
mean the
Yeah,
painting of the
that's
bars won't have an influence on the choosing of the car.
yes. So that's the common sense, right? So people won't like for this case, the painting won't have any effect about the utility, like unless there will be some specific person who have some specific favors about the colors. But for general case, if we just consider car and bus will be transportation mode, then you repaint the bus, won't change the utility of the bus, won't change the utility of the car. So from the common sense, the probability of choosing the bus will still be half. Probability of choosing car is also be the half. But if we go to check the multinomial logic model, for the utility of the car it's still be V, right? We did not change the utility of the car. For the red bus is also in the bus, so the utility of choose the red bus is also V. And for the blue bus, it's also in the bus, so the utility for choose the blue bus is also V. Now it becomes very strange. If we go to apply the multinomial logic model, well, to calculate the probability, we have three modes. The utility for each mode is V. So car is V, red bus is V, blue bus is also V. So what you can get from this analysis, from the calculation, you get the result as the probability of the car is 1/3. Just quickly from this calculation, probability of car is 1/3, probability of bus is 1/3, and probability red bus is 1/3 and blue bus is also 1/3. So if we do this kind of calculation, the probability of bus, like the probability of choosing red bus plus the probability of choosing blue bus becomes 2/3, and the probability of choosing car is 1/3, still 1/3. So like you just repaint the bus, you get more people taking the bus, and that's actually unreasonable. It's not realistic. So this one is not realistic. In our common sense, it still be 1/2 for car, 1/2 for bus. So now the problem for this one is like we cannot apply the multinomial logic model to this specific problem directly because the IIA property is not satisfied. So in this case, the red bus and the blue bus, they are not independent to each other. Instead, they are actually correlated with each other, highly correlated with each other. So for this specific case, if the independence property is not satisfied, then we cannot derive the we cannot use the equation. We cannot use the equation from the multinomial logic model directly. We need to find out an alternative method. So that means that it violates the assumption 3, and the random term is not random for it's not independent for now, and we cannot define these three modes to say that red bus and blue bus are independent, and then apply the multinomial logic model directly. So to do that, we will need to we can try to explore what's the go back to check what's the what happens here. For the red bus and blue bus scenario, the random terms are actually highly related with each other. So we will have covariance for the red bus and blue bus. Say that is also pi square divided by 6. And then we we need to carefully think about how to define a new structure. Also here it's like the red bars and the blue bars are some extreme examples, but in reality there will be a lot of other examples that are not that extreme. For example, for the public transit mode selections, you will have the options of the bus, the express bus, and the rail. This will be the three possible options, but you can consider that the bus and the express bus, they are not 100%, they are not independent of each other. So you cannot consider them as three independent modes in the multinomial logic model. And similarly for the car and carpool, they have some correlation with each other. It also can be applied for the route choice. Like for the route choice, it's if we want to drive from Toronto to Hamilton area, you can choose the QW plus 403, or you can choose 403 directly. But there will be some overlap about the routes to use the 403. So it's still not the 100% independent to each other. So those would be some realistic problem, and we need to make sure that the independence features is satisfied before we record the multinomial logic model. So with that, we conclude that if we want to address this problem, we can use the multinomial probability model. That's a different type of the model, or the nested logic model. That will be something that I'm going to introduce for the next slides. So these two can help us to handle the case when the variables are not 100% independent of each other. So now let's first go to check the multinomial logic, the multi-dimensional choice problem, and especially focus on the nested logic model. So here, let's consider the this is one kind of extension about the multinomial logic model, where we're going to work on different more than one dimensions of the modes or the alternatives that are not independent of each other, and we call them as the nested logic model. So we will put the we'll consider a set of the alternatives nested under one parent alternative. So to give you more introduction about that, let's first go to see the start with some simple case about the joint decisions with the multidimensional logic model. So in the transportation system, we can consider the when you work on the decisions, you will usually consider two different decisions, two common decisions. One is the mode. What kind of mode are going to use? Are you using the car? Are you using the bus? Bike, walk, and so on. And also it involves with the destination selections. If you want to go to the shopping or you go to the supermarket one, some grocery store, or some local farmers market, and so on, this would be the your destination choices. So those are all the decision problem, and you need to make your decision, making a joint decision about the mode and also destinations together. So that will be more complicated than what we discussed previously. So here, let's consider. Let's just start with this consideration. So here we will have two sets of the choices, C1 and C2. C1 says that C1 is for the mode, and C2 is for the destination. Then the joint decision will be C1 times C2. Say that this is a C star. For the no, sorry, not a C star. And the joint combination would be C1 times C2. That will be the total combination. And we also denote set that Cn star is the subset from C1 times C2. That is not available for the individual n. So for example, for some individuals, they don't have the car, so they cannot drive their car to the grocery store. They can only take the bus or the train. So we need to exclude the car from the from your choice set. So with that, the actual choice set of the for the individual n would be C1 times C2 minus Cn star. So that's the total choice set. And now let's go to see an example. For the mode decision combination choice, we have the set of the mode M1, M2 to MJM. And we also have the set of the destinations D1, D2 to DJD. And we can find out all the possible combinations. That will be M times D, which will include M1, D1, M2, D2, M1, DJ, M2, D1, M2, D2, and so on. And we also assume that a set of the mode is not available for the individual n, say that M1, D1, M1, D2 are not available. M1 DJ is also not available, which means that for the mode M1 is not available for the individual n. Then we can find out the combined the actual decision, the choice set for the individual n, which would be C1 times C2 minus C1 minus Cnk. So that is, in this case, that will be M times D minus Cn star. With that, we have the decision set that is available for the individual n. So with that, we have the decision set for the for each individual, and then we can try to find out the model to estimate what's the probability for the individual n to choose the combination of the choice. So here we have the we said that all the Cn is all the mode destination combinations for the individual n, and we assume that the probability of Dm would be the one for the individual n to choose the destination D and the mode n. Also, we define the utility for the mode destination combination Dm, that is UDN for the individual n. And for this utility, we assume that it consists of four components. One is the VDN, that will be the utility from the destination D. VMN is the utility from the M, and the VDM is the deterministic utility from the combination from D and M, and epsilon dm would be the random term for that combination. And in this model, if we consider two different combinations, dm prime and dm double prime, you can see that, which I can write in these two equations. You can see that these two variables for the deterministic component from destination D will be the same for these two combinations. And in that case, we say that VDN will be the shared observed attributes. And for these two mode, you can also see that for the random term, they are actually different to each other. For the first one is the epsilon dm prime. The second one is the epsilon dm double prime. So those are two different random components. And in this case, we say that these two combinations does not share the random components. And so for now, based on these assumptions, if we assume that the epsilon dm follows in the Gumbel distribution, the standard Gumbel distribution, we can find out the probability of choose the combination d and m. That is exponential of the vd plus vm plus vdm divided by the summation of that exponentials for all the combinations. And here, well, for the following derivations, we will try to use there will be another note. We'll try to use some dummy variables to summarize as in the summations, so that you will not be confused about the variable we specified in the other components of the equation. And now, with the defined probability for the combined decision, we can then calculate the marginal choice probability, which would be the probability of choosing the mode D, or the probability of choosing the mode choosing destination D, or the probability of choosing the mode M. The derivation will be very similar. So for the probability of choosing the mode D, that will be the summation of all the modes under the with respect to the destination D. So it's a summation of the probability of dm given md. And we can then for this for the example we can here md is the set of the mode available for the individual n to assess the destination D. If we go to check the our example for the previous example, we have suppose that we have 3 different modes, M1, M2, M3. We have 4 different destinations, and the complete mode destination combination would be 3 by 4. That will be we have 12 different combinations, but we assume that 5 of them will not be available. M1, D1, M1, D2, M2, D1, M2, D3, M2, D4. They are not available. Then we can find out what's the choice set for the for each individual to choose the destination D. So for MD, so MD1, which would be the mode available for the destination D. If we go to check the decision choice set, you can see that only mode 3 will be able to send you to the destination D. And similarly for the destination 2, you can find out the mode 2 and mode 3 is available. The mode 1 is not available. And similarly for destination 3, that will be mode 1 and mode 3. And destination 4, that will be mode 1 and mode 3. So we have this set of the mode available for each destination. And then we can use this information to calculate the marginal choice probability with the probability of the destination D. So still we can try to recall the multinomial logical model for the combination, the probability of D and M. So it's related to the all the deterministic utility. And now you can get the you can apply the definition of the marginal choice probability, put them together. With that, you can follow this derivation. We will actually be able to find out a very simple expression for this marginal probability. So basically, if you put all them together, you will find out the probability, the marginal probability of D as this big formula. But if we make an assumption if we define a new variable, say that the log sum variable, we call this as a log sum term for the a log sum term for the marginal choice probability. With the exponential of this log sum term, it will just be the summation of exponential Vm plus Vdm, and if we put them there, put them in this equation, you will get the result as the marginal probability exponential of the Vd plus Vd tilde divided by the summation of exponential Vd prime plus Vd prime tilde. So here, this Vd tilde is the one we defined as the log sum term, so that we can simplify the calculation of the marginal choice probability. And this one is also this log sum term is also very important for us to conduct the calibration of this joint logic model or the nested logic model. So now let's give more details about the log sum term. So for the let's first consider a set of the alternative A, and we assume that the expected value of the utility is chosen from the alternative. It's set as UK. If we choose the one from this set of alternative, that will be the utility will be the maximum one of all the different alternatives in the set. So that's what we always assume for the discrete choice model. And now we can find out what's the probability distribution of the U star. So to do that, the probability of U star for the cumulative distribution function, that will be the probability of U star is less than smaller than X, which means that for all the utilities, it must be smaller than X. And we know that the utility is the function of the deterministic components and the random components. The random components is assumed to be in the Gumbel distribution. And also, we know that the all these random terms are independent to each other. So this utility, this probability will be the product of the probability for each random term smaller than X minus Vk for each alternative. And with the Gumbel distribution, by assuming the Gumbel distribution, we can derive the expression for the this cumulative distribution function. If we do this estimation, you can find that the CDF will be the exponential minus summation of exponential minus X minus Vk. So that's the formula for the cumulative distribution function. And now let's see how it can be connected with the log sum term. So by using this one, from this equation, we can actually take the exponential of minus X out of the summation, and by assuming that the exponential of the summation of this exponential term as an exponential of the log summation term, you can get the simplify the formula as exponential of minus X minus log summation of exponential Vk. So this one, if we go back to check the Gumbel distribution, this means that this one follows the Gumbel distribution with the line summation of exponential Vk for the mu, and eta is still be1. So we can then find out the mean value. We find out the mean value of this distribution, and get the expected value of mu as log summation of exponential vk plus gamma. Gamma is an Euler constant, and that's what we get for the that's what we get about the log sum term in the gamma distribution, and we can see that the log sum term is measures the expected utility derived from the choice set with a set of alternatives. It just measures the expected value, expected utility of this choice set or this choice problem. And this is what we get from the this is what we define for the log sum term, and then we can see that in this case, in this specific problem, VD tilde measures the expected utility derived from the choice problem involved with the alternative mode that can access to the destination J. It will be the expected utility for all the different modes to the destination J. So that's what we define for the log sum term. And also there will be another way for us to derive the marginal choice probability. I will just skip that. It's basically we can use the property of the gamma distribution to get the result. So if you are interested about the details, you can try to see the detail or try to see the go to check the animation here and try to see how the gamma distribution, the maximum value of multiple gamma distribution can be used for us to get the probability. So what we get, eventually we get the same result. So I'll just skip all the steps. So eventually we get the same distribution, same formula for the marginal choice probability. And here we have log sum term. This is about derivation about the marginal choice distribution probability with respect to the destination D. If you apply the similar procedure, you can also find out the marginal probability of choosing the mode M regardless of the destination. And here, in this case, the log sum term will be related to the will be the expected utility for all the destinations that can be assessed with the mode M. So that's what we get for the marginal choice probability. And another thing we want to derive from this for the joint logical model is the conditional choice probability, which will be the probability of mode M given destination D, or the probability of the destination D given the mode M. And that one, to do this kind of analysis, we need to recall the Bayes theory. For the Bayes theory, we have the model, the probability of mode M given the destination D is the probability of the joint or the combined mode destination divided by the probability of M. So we know the joint probability. We also have already derived the probability of the marginal probability for the destination D, and then we put them together. We can quickly find out the formula for the conditional probability. So this is what we have for the joint probability, and we have the conditional probability. Not the marginal probability. We will put them together. We'll put them together and then try to apply some simplification. Again, I'm gonna skip the details. There will be a lot of components can be removed from this very long and complicated formula. And once you do some expansion about the components, the log sum term and the variables we defined, you can get a relatively simple formula for the conditional probability. So what do we get eventually? I'm going to skip those steps. Eventually, you will get the conditional probability for the destination D given the mode M as exponential of Vd plus Vdm divided by summation of the exponential of Vd prime plus Vd prime M. And similarly, we can find out the conditional choice probability for the mode M given the destination D. You just need to change the index with respect to the destination and the mode a little bit for these two equations. So that's what we derived for the joint probability, conditional probability, and the marginal probability. With that, I will summarize them together in these slides. So for the joint logical model, we have the joint probability to choose the mode D and destination M. You can see the formula here. They're all related to the deterministic component. We will also be able to find out the marginal probability, and that will be the marginal probability for the destination D and the marginal probability for the mode M. And to identify each probability, you have to specify the log sum term with respect to each mode and each destination. And also, we have the conditional probability for the destination D given the mode M, and also the mode M given destination D. All of them will be very simple, and it could be once you have already calibrated the functions for the deterministic components, it will be quite easy for you to get all these probabilities. So that's the some features about the joint logical model, and I think we reached to 410, and I would like to take a short break here for 10 minutes. And before I start the break, do you have any questions about the introductions of the multinomial logic model, especially the multidimensional model?
Yes, Professor. I have a question about the multidimensional logic.
Yes.
So basically, when we have in the one dimension multinomial logic, we have Cn equals, say, car, bus, and cycle, let's say. But in a multidimensional, you will have, say, shopping mall with car, shopping mall with bus, shopping mall with cycle. So basically, the only thing difference is just the choice set will increase in the dependent variable will still be Cn. But
yeah, it's like there will be more multiple dimensions. Like usually the say that the destination and the mode will be two different decisions, but we can consider them as the separate decisions. But for each individual, it's actually combined. If you make a decision about doing some activity outside go to shopping, you have to decide which shopping mall you have to go, and which mode you have to take. So for yourself, for each individual itself, is not combined. It's a combined decision.
okay.
Yeah, that's the reason. Yeah, that's the reason we want to introduce this kind of multidimensional logical model, and also there will be a lot of it will become more and more complicated. This one it's the most complicated. The one that I introduced about joint logical model is the most complicated. It's the most complicated scenario. Like we assume that all the combinations are independent to each other, but in the other case, some of them are not independent to each other. So with that, we have to introduce the nested logic model. That's what be something I want to introduce in the rest of this slides, rest of this lecture. Yeah.
Okay. So basically, the effect of choosing car based on shopping mall location, it is basically we define it first that it is we consider it as a combined decision. Like it is also a choice,
Yes.
like a mode choice, basically.
Yes. 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 Yeah. It's kind of a way to simplify the your analysis for a very complicated problem. Even though the model looks like more complicated, but the regarding to the computational cost and the data collection perspective, it's I mean gonna be most it will be more cost effective.
Mhm. Okay. Thank you.
Okay. Okay. With that, I will just stop here and taking a break, and we can resume our meeting at 4:23 for 10 minutes. Yeah. Okay, let us resume the meeting. Let me see whether this one is working or not. Just a moment. Just a moment. Let me stop sharing. It happens again. Okay, it's working. So we just introduced the joint logic model with the all different kind of probabilities, the joint probability, marginal probability, and conditional probability, and we can. So this is based on the assumption that we only have one random term for each combination. But in reality, these things can be more, the problem can be more complicated. Sometimes we will share some unobserved attributes. For example, we still consider the mode destination combination choice. We have a set of mode destination combinations, and we can find out the probability of selecting a combined mode destination. And we know the utility of that combination is in the summation of the deterministic component and some random components. So here in this new definition, we have three deterministic components, which is the same to what we showed previously. But in addition to that, we will have two random components that is applied to the each to the destination. That is epsilon d, and also the mode, that's epsilon m. And these two random components will be something unobserved random attributes. And so we call this one as, like, if we still consider the same two different combinations, d and m, dm prime and dm double prime, then we will have two shared components. Vd is the shared observed component that can be obtained from the real world attributes. And the epsilon d is the random component that cannot be observed. So if we have this assumption, we need to think about how we can build a model to estimate the decision based on the this additional unobserved shared attributes. So to do that, we can actually make some assumptions by assuming that either epsilon d or epsilon m is 0. So depending on what kind of which one you want to choose as the shared attribute or the shared component, unobserved component. So for example, let's just assume that the epsilon m is 0. So it's we can remove the epsilon m from the utility equation, and with that we have the utility of the combination of d and m as vd plus vm plus vdm plus epsilon d plus epsilon dm. So we have two random terms here. And now we need to build the model based on this new utility function. And that is the nested logic model we defined. First of all, we have to, similar to the previous step, we have to calculate what's the marginal choice probability. So that is the probability of choosing the mode D. And this one, for this derivation, we can actually use the still use the property of the Gumbel distribution. So we will try to find out the maximum value of the utility for the set of the choice to the destination D, and this would be the here we can get the all the equations of the utility, and we can pick up the common variable out of the maximization. With that, we will then apply the Gumbel distribution, assuming that the epsilon dm follows the Gumbel distribution with the parameter of 0 and mu dm. And then for the from the force property of the Gumbel distribution, as we showed previously, we can find out the distribution of the components inside of these brackets, and that one give you the give you the distribution, a new distribution with the two parameters Vm plus the Vdm and mu dm. And then we can also apply another feature of the another property of the Gumbel distribution. That is the sixth property. We also showed that one in our previous slides. We can then find out the probability of the Gumbel distribution for the maximization problem, and then it could be right into a new Gumbel distribution. And after that, we're gonna see what happens for the what gonna happens for the whole utility function. For the whole utility function, we will recall the property 4 again, and eventually we're gonna get we find that the I'll jump to the final conclusion. So eventually we're gonna find out that the maximization of this one follows in the Gumbel distribution, and there's a random term epsilon d star. It's in the Gumbel distribution with the parameter of 0 and mu dm. And this is what we get for the utility for the maximization of the utility, and now we put them in this equation. We can then calculate the distribution of the marginal choice probability. By knowing the distribution of these two random terms and also the distribution of the shared and observed attribute, we can easily get the distribution, the probability. Not exactly easily, but we can use the features of the Gumbel distribution to get the result. Again, I'm gonna skip the derivations. You can try to check the details about the derivation after class. So once you complete all the derivations, we can get the probability, the marginal probability. Let me jump to the final conclusion. So it will be a very simple equation. So we are in the once you finish everything, you can get an marginal choice probability with this equation. So the probability of choosing the destination D is exponential mu D times Vd plus Vd tilde. Vd tilde is a weighted log sum term. It's quite similar to the sum term that we log sum term we defined previously, but here we need to consider the parameter mu that we defined for the mu dm that we defined for the random term epsilon dm, and this would be the two additional parameters we need to estimate. It's actually don't know. For in the model, we have no idea about what's the value of the mu d and the mu dm. We need to calibrate these two variables with the real world data. But once you have these two variables and the calibrated equations for the utility, the deterministic utility, you will be able to find out the marginal choice probability. And similarly, you can also find out the marginal choice probability if we choose for the mode. But you can just simply modify the index to get the similar result. And so that's for the marginal choice probability. We can also work on the estimation of the conditional choice probability. So that will be the probability of the mode M given the destination D. So here we assume that the either epsilon D or epsilon M is 0, and similarly we use the epsilon M as 0, and we have the deterministic the definitions of the utility function, and for the utility the probability of the conditional probability of M given D is the utility of the UDM is higher than utility of the UDM prime, where M prime belongs to all the other belongs to the set for all the alternatives available to access to the destination D. And if we try to apply the utility function here and recall some features of the Gumbel distribution, we can get the we can quickly get the formula for the conditional choice probability, which is relatively simple. So we have the probability as exponential mu dm times Vd plus Vdm divided by the summation of the exponential values. And again here, mu dm, it's something we don't know. It's something we have to calibrate from the real world data. So that's the conditional choice probability, and with that we can then estimate what's the joint choice probability. So this one is a little bit different from the previous one, the joint logic model. In the nested logic model, we have to use the conditional probability and the marginal probability to estimate the joint value. So again, we're going to need to use the Bayes theorem to calculate the joint choice probability. So here the joint choice probability will be the product of the marginal probability, the conditional probability and the marginal probability. So we already derived the formulas for these two. So with that we can get the the joint probability as shown in this equation. It's quite complicated, and again we also need to use this one. We have to use this one to calibrate the nested logic model. So that's all the background information about the nested logic model. And the next thing we need to learn is about how to build the structures for the nested logic model. So here are some rules for us to build the model. Assuming that we have two dimensions, the mode and destination, and we want to build a model for these two levels. And with that, we can first assume the which kind of random terms we want to remove. Similar to the previous analysis, we remove one random term, epsilon m, for the mode m, in the utility function. So we will only have two different random terms, epsilon d and epsilon dm. Now, we can build the two levels for this nested logic model. The first level will only work on the destinations. So we will have JD different destinations, and and that's actually the destination set. And for each destination, there would be multiple choices of the mode, and we call this one the lower level, or the level 1. And this one is called this one is defined as the destination set for each, the mode set for each destination. In each level, there's one random term. So for the level 2, we only consider the destination. So there's only one random term, epsilon d, and the random term for the mode is set at 0. And for level 1, we have another random term, epsilon dm, because for each destination d, there's there are multiple modes, and for each destination and mode combination, there's one random term, that is the epsilon dm. And so basically for the nesting structure rule, for the random term for all the error term at any level does not involve with any any other dimensions at the lower levels. For example, for this case, in the level 2, we have the destination. We only have destination. The mode is under the lower level, so we don't include the mode in the random term. This rule should be applied for the more complicated case with more than 2 levels. We have, if we have another thing like the route, we're gonna introduce that one later. Then level 2 will not involve with the mode and the route, and for level 1, it will not involve with the route, and so on. So that's the rule, the most fundamental rule we have to consider. And we also can have the extension for the 3, as what I just explained, for the higher dimensions. We will consider the combinations of the mode, destination, and the route combinations for what kind of destination you want to take, what kind of transporting mode you want to use, and which route you want to take to reach your destination. So with that, we will have 3 dimensions, which means that we're going to need to set 3 levels. And so we have to, assuming that we set the first level, the top level as the destination, followed by the mode, and then followed by the route. Then we can actually have 3 levels. In level 1, we will have we will only have the error terms for the destination. We set the epsilon m and epsilon r will be 0. And in level 2, we will only have the epsilon dm for the destination and mode combination. For the epsilon dr and the epsilon mr will be set at 0. And for the level 1, the lowest one, it will involve all the levels, all the 3 levels. So we have the epsilon dmr. With that, we can write down the utility function. So for the utility function, we have utility for the combination of dmr will be vd plus vm plus vr. So that will be the deterministic component for each dimension. We have the vdm, vdr, vmr for the combination of any 2 dimension, and the vdmr for the combination of all the 3 dimensions. And regarding to the random terms, we only have 3 random terms applied: epsilon d plus epsilon dm plus epsilon dmr, as what we set for this nesting structure. So that's one example. We can also have another type of the nesting structure. For example, we can put the mode at the top level, followed by the destination, and then followed by the routes. So with that, we will in level 3, we will have the error term of the epsilon m. For epsilon d and epsilon r, it will be set as 0. And for the level 2, we will only have the epsilon dm. For the level 1, we have the epsilon dmr. And if we put them together, you will get an you can get the utility function. The deterministic component will still be the same, but we have the new definitions of the random term. So here we have epsilon d plus epsilon dm plus epsilon dmr. So that's the another method, another structure. And of course, you can go to find some more even higher structures if you want. And now, if we want to extend this one to higher dimensions, like for this case, for the 3 dimensions, we will need to find out a way to calculate the probability. So we have to make some assumptions about the random term. So first of all, for the error term epsilon d, we assume that it follows the gamma distribution, but instead of the standard gamma distribution, we assume that it follows the gamma distribution with the parameters of 0 and mu d. And similarly for the other 2 variables, we assume that it follows the gamma distributions of 0 for eta and mu m, 0 and mu r for epsilon dmr. So here we have 3 variables that we assumed for the gamma distribution, and that will be the variables we have to estimate from the for the calibration in the calibration process. And with this assumptions about the gamma distribution, we can then go to the estimation about the probability, the joint probability of the combinations for the 3 aspects: mode, destination, and then routes. For the estimation of the joint probability, again we have to recall the conditional probability and the marginal probability to get the results. As this would be the 3-dimensional problem, we have this joint probability will become the conditional probability of the route r given d and m times the probability of the conditional probability of the m given d times the marginal probability of the destination d. And we can then first go to see how we can get the the expression for the conditional probability of r given dm. I'm going to try to skip all this process. If you're interested about derivation, you can check it after class. It comes from the very complicated utility function, but there will be a lot of common variables can be removed from the derivation. I'll try to jump to the destination, the final formula directly, and this one shows the expression for the conditional probability of r given d and m, and then we can go to check what's the conditional probability of m given d. So again, here we have to recall the formula from the property of the gamma distribution. Well, I will try to skip most of the details. If we follow these instructions, and eventually you can find out a relatively simplified formula for the conditional probability, where you can get the conditional probability of m given d as shown in this formula. And here we have to consider the log sum term from the lower level. Basically, you need to find out the log sum term for all the deterministic components related to the route, related to R. So you can see that you need to consider the deterministic utility of VR, VDR, VMR, and VDMR. So all the deterministic components involved with the route R should be included in the log sum term. So that's the the second conditional distribution. And similarly, if you try to do some expansion, you can get the marginal distribution is the same to the one that we derived for the joint logit model. So we can, I'll just skip it here. So that would be the nested logit model. It's just, I know it's quite complicated, so I'll just give you some ideas about how the nested logit model is designed and what's the features of it. In the for the project that you do and for the homework, you will not be asked to work on the multi-dimensional logit model for more than 2 dimensions. You will only work on either 1 dimension or 2 dimension. So that's some theories about nested logit model. The next thing we want to consider is how to conduct the estimation or calibration of the nested logit model. So the so let's consider the first consider the 2-dimensional case. This algorithm can also, this logic can also be extended to 3 or more dimensions. So first, for 2-dimension scenario, we still consider the mode and destination combinations. The utility will consist of 3 deterministic components and 2 random terms. From the nested logit model, we set level 1 as the mode and level 2 as the destination. So assuming that epsilon m as 0, and now we can get the we have already derived the marginal probability, which is related to the utility of d of destination d and the log sum term for the destination d. And here, this is the expression for the log sum term. It's calculated based on the deterministic component of the for all the deterministic components related to the mode m. And we also have the conditional probability for m given the destination d. It gives us the result. Is for this formula, we do not have any log sum term, but we have the additional random additional unknown variable mu m, which would be the one for us to determine the distribution or the Gumbel distribution for the random variable epsilon dm. And with that, we can find out the joint. We can find out the joint probability by the product of the conditional probability and the marginal probability. And then we also assume that there exists a linear relationship between the deterministic component, deterministic utility, and the attributes. So Vm equal to beta m times xm, Vd equal to beta d times xd, and Vdm equal to beta dm times xdm. So beta m, beta d, and beta dm will be the coefficients. The coefficients applied for us to estimate the deterministic component, and xm, xd, and xdm will be the attributes for the estimation of each deterministic component. And also, in order to conduct the estimation, we will apply the likelihood. We will use the maximum likelihood function. We'll apply the likelihood function and the potential log likelihood function to get the result. Basically, we want to maximize the probability of the sample as what we observed. So at first, we will formulate the likelihood function. So basically, that will be the products of the probability for all the observations. And again, here, ydm equal to 0 if the individual choose the combination of the destination d and the mode m. So this is the likelihood function, and we know that it's very complicated. So we have to find out a way to simplify the maximization problem. So to do that, we will try to do the log transformation to find out the log likelihood function, and change the product sign to the summation sign. And also for these two components, for the probability, it actually can be written into the summation for the two log probabilities. So with that, you can write this log likelihood function into two components. One is related to the conditional probability, the other one is related to the marginal probability. And we can try to maximize this log likelihood function. We can try to work on the maximization for each one of them independently. So we can start work on the maximization of the term 1, and then work on the maximization of term 2. So now let me give you more details about the how to get the maximum, how to find out the optimal parameters. So we have already derived the formula for the conditional probability. So this is the one we get, and we also know the formula for the marginal probability. And here there's an log sum term. So if we put them in the logs in the log likelihood function, and we also replace the deterministic component with the linear formula as we assumed. So we have Vm equal to beta m times xm, Vt equal to beta d times xd, Vdm equal to beta dm times xdm. And now put this expression in this formula. It makes the equation gets more and more complicated. But let's try to work on this one to stay with this long equation to work on the estimation. So there are several steps for you to conduct the calibration or the estimation of those parameters. First of all, we're going to work on the mu m times beta m and mu m times beta dm. So we will work on the first component. Work on this part. As we mentioned previously, we want to maximize this component, the term 1. To do that, we first assume that mu m equal to 1, and then we're going to estimate mu m beta m and mu m beta dm, which will just be beta m and beta dm. As in this equation, all the variables, the xm, xdm, they will be available for us to observe. We also can find out the value of the ydm. That will be the choice of the each individual. So we will be able to find out the value of beta m, the value of beta m and the beta dm as the beta m hat and beta dm hat. And this kind of method, this estimation, is the same to the one that we showed previously for the multinomial logic model. It's exactly the same. We will just have more variables to calibrate. And once you have these two values, you have these two variables. Once you have these two coefficients, beta m and beta dm, you're going to use that one to calculate the log sum term. So beta vd tilde hat. So we're gonna apply this equation to calculate the log sum term. We assume that the beta mu m is 1, and we have the value of beta m hat and beta dm hat. So we will be able to find out the log sum term for each destination d. And now, in the third step, In the third step, we're going to work on the maximization of the second component. We have already maximized the first component based on the from the step 1 and step 2. And now let's work on the third step. In the third step, we can assume that VD tilde hat is an independent variable to XD. And with that, we can then estimate the parameter of mu d times beta hat and mu d hat. So that will be the two variables here. You will have in this equation, you know what's the value of XD. You also have already estimated the value of the VD, and then you can actually apply the same thing to multinomial logic model to find out what's the value of the mu d times the beta d, and the mu d. And with that, you know what's the value of the mu d and what's the value of the beta d. So that's the process for you to get the parameters in the second component. So basically, for the in the step 3, you're going to try to summarize all the variables related to the destination D, x1, x2, x3, get xjd, and add an additional log sum term. So vd for the to build a linear equation to calculate the deterministic component. So that's how the estimation is conducted, and it will be relatively complicated. So you just need to know how it's working, and it's not necessary for you to manage the details. And so in this estimation, you will also be able to find out the value of the mu d. This one is just based on the multinomial logic, the calibration method of the multinomial logic model, and they can be quickly it's just performed as the one variable, one coefficient for us to obtain. So with that, we have conducted the estimation. So once we have the mu d times beta d is mu d times beta d divided by mu d, and that won't give you all the steps to work on the calibration of the nested logic model. So with that, we can make a quick summary about the calibration. So first of all, we have the probability for the combination of the mode and destination, and we specify we defined the utility function with the two random terms, epsilon dA and epsilon dm, and then we have the assumptions about the linear equations for the deterministic components of the utility function. And now we will divide the joint probability into two components, the conditional probability and the marginal probability. In the marginal probability, we will actually be able to find out the log sum term, and in the log sum term, and then for the calibration, in the first step, we will try to maximize the first term. And in the first term, is able to give us the result of beta m and beta dm. We also assume that mu m is 1. And now from the second step, we're gonna calculate the log sum term. After that, in the third step, we're gonna calculate what's the value of the beta d and mu d. So these two values. with that, we have finished the calibrations of all the coefficients for this two-dimensional nested logical model. So that's the general process. But if we have the extension to three-dimensional or even higher, even higher dimensions, we also need to have some ideas about how to extend the calibration method to that complicated problem. So first of all, we here I'm just introduce the three-dimensional case. So for the three-dimensional case with mode, destination, and route, we have a utility function defined with the three random variables, epsilon d, epsilon dm, and epsilon dmr. And we assume that epsilon d is the Gumbel distribution. Epsilon d is Gumbel distribution with zero with the with the zero of 0 and mu d, we have for the epsilon dm with Gumbel distribution of 0 and mu m, and the epsilon dmr it's 0 and mu r. So that's our assumption about their distributions. We have also derived the formulas for the conditional probability with r given d and m, the conditional probability of m given d, and the marginal distribution of d given for the destination d. And here you have to know how the formulas for us to calculate the log sum term for the higher levels. And from Bayes theorem, we will be able to find out the joint probability with these three conditional and marginal probabilities. And that's all the preparations we need for the calibration. Also, we assume that there exists a linear relationship between the observed attributes and the deterministic utility functions. And here we have seven deterministic utility components. So there will be 7 variables. And regarding to the set of the parameters we have to calibrate, that will be the beta m, beta d, beta r, beta mr, beta dr, and beta dm, and the beta dmr. So those would be the coefficients we have to calibrate. And to conduct the calibration, again, we're still gonna need to use the likelihood function, and we will try to maximize the joint probability of the observations from the sample. And again, we have to replace the joint probability with the conditional probability and the marginal probability. Similar to the two-dimensional case, we will also apply the log transformation to get the log likelihood function. And if you apply this log likelihood function, you can see that this equation will be divided into 3 terms. The term 1 will show the lowest level 1, about the with respect to the probability of the route given the destination and the mode. Term 2 is about the mode m given the destination d, and term 3 is only about the destination. And again, if we want to do the maximization for this one, we can try to maximize each one of them. We'll start from the term 1, go to term 2 and term 3. So let me show you some details about the procedures to conduct the calibration. First of all, we have to need to replace the conditional probability and joint probability with their full formulas, and let's just put them in the equation in log likelihood function. And for the calibration process, we start with the term 1, and then go to term 2 and term 3. In this first step, we will try to estimate the parameters of mu r, beta dr, beta mr, beta dmr. And similar to the two-dimensional case, we assume that mu r is 1. With that, we only need to estimate, we can find out beta r, beta dr, beta mr, and beta dmr as the head for in this statement. And in this estimation, all the variables are known. All the variables can be obtained from the samples. We know the value of the XR, XDR, XMR, and XDMR. We also know the values of the YDMR as the selections of the individual. So we can calibrate this one with the just like what we do for the multinomial logic model, the same calibration method. And now that's the once we finish that, in the next step, we're going to calculate the log sum term in the second component. So we're going to move to the second term. We have already obtained the value of the beta r, beta dr, beta mr, and beta dmr. So we can just recall the definition of this log sum term to get the value of their value and put them in this second term to do the calibration. Once the log sum term is estimated, we're gonna consider the VDM tilde hat as an independent variable, and with that we can find out the estimated value of the mu m times beta m, mu m times beta dr, dm, and mu m. So it's in this component we know we can observe the value of the xm, xdm. We calculated the log sum term, so it's capable for us to get all the coefficients. Again, I say that we're going to use the same method as the multinomial logic model to do the calibration. And similarly, in the first step, we will have to calculate the log sum term for the third component, that is VD tilde. So we from the step 3, we get the value of mu m, beta m, beta dm, and also the value of the VDM tilde hat. Then we can just record the definition of the VD tilde to get the estimated value. And with the estimated value, we can do the similar process to the step 3. Consider VD tilde hat as an independent variable and apply and using this marginal probability to get the value of mu d times beta d and mu d with the calibration of the multinomial logic model, and then we can find out what's the value of the beta d. So with that we have found out all the values, all the coefficients. This step can also be extended to even higher dimensions. So you can go to the step 6. If you have you have 4 dimensions, you can go to step 6 to calculate the log sum term, and then step 7 to do the calibration. If we have furthermore dimensions, we'll repeat this process until you finish the calibration of all the coefficients in the log likelihood function. So with that, I think I finished the introductions about the log likelihood function. And now the next logic model with the calibration from the log likelihood function. Do you have any questions about that? It will be relatively complicated when we have the computational complexity will increase dramatically with just one increase of the dimension, and especially if we try to think about the linear models for each deterministic component. Like for the for 2 dimensions, you only have 3 equations, but for the 3 dimensions, you have 7 equations, and for 4 dimensions, this number will increase exponentially. So it's really hard to conduct the calibration with high dimensions. There will be some publicly available sources online for you to do the calibration for the nested logic model. And if you're interested, you can try to search online. It will help you to finish the calibration automatically. Okay. Any questions about this one? If no, I will go to the next one. The next model to deal with the this kind of complicated a more complicated situation without any independence of the random term. So that one is called the probability model. It's one model that is different from the logic model. In the logic model, we assume that the random term follows an Gumbel distribution. This is just one assumption, but we also can assume that there's another distribution of the random terms, and with the probability model, we usually assume that the distribution it follows the normal distribution, which is commonly applied. In addition, we assume that those random terms are not necessary to be independent of each other. So we accept that there are some covariance or coefficients, co-relationship between the among multiple random terms. So let me first give you the background about the probability model. We start with a very simple, the simplest probability model, that is the binary probability model, where we only have 2 alternatives. So consider that there are 2 alternatives, either the choice 1 or choice 2, and we also know the utility function. So for the utility of the choice 1 is V1 plus epsilon 1, and the utility of for the choice 2 is V2 plus epsilon 2. So here V1 and V2 are the deterministic components, but for the random term, it's epsilon 1, epsilon 2. We assume that it follows the bivariate normal distribution with the mean of 0 and covariance of epsilon and the covariance matrix. So for the covariance matrix, with that we can find out the we can use that distribution. So for the distribution of this equation shows the distribution of the bivariate normal variables, and the mean value is 0, and we are provided with the we are also provided with the covariance matrix. So with that, assuming that the covariance matrix is sigma 1 square, sigma 1 2, sigma 1 2, and sigma 2 square for the 2 different variables, and with that we can calculate the probability of choosing the alternative 1. So if you choose alternative 1, means that the utility of 1 is higher than utility of 2. And in this case, if you apply the utility function in this probability, which will give you the result as the probability of the epsilon 1 minus epsilon 2 is smaller than V1 minus V2. So that's the probability we can calculate for the alternative one. As we are provided with the distribution of the epsilon 1, epsilon 2, then it's possible for us to find out what's the exact value from this one. And this kind of method is called the probability model. So now let's see how we can calculate the probability. So first of all, we know that epsilon 1 and epsilon 2 they have their mean 0, and we know their variance. But if we go to check the difference of these two variables, epsilon 2 minus epsilon 1, it's also a normal distribution. And the variance of this one, epsilon 2 minus epsilon 1, should be sigma square, and that is a sigma 1 square plus sigma 2 square minus 2 times sigma 1, 2. So then by knowing this distribution, so it's this one is a normal distribution with 0 and sigma square. And by knowing this distribution, we will be able to find out the probability. So that is it's a phi v1 minus v2 divided by sigma. So that's the cumulative. This is the cumulative normal distribution. The phi is the cumulative normal distribution. If we have already calculated the value of v1 and v2, and we know the value of sigma, we can easily get the probability. So now let's go to check one example, one specific example. Still, we have two alternatives. We know their utility function. We get the deterministic utility as 6 and 7 for the choice 1 and 2. Also, we will be provided with the distribution, the functions of the distributions of the random term with the as bivariate normal distribution with the mean of 0, and we are provided with the covariance matrix. Say that it's 0.5 for sigma 1 square. This is a sigma 1 square, and sigma 1, 2 is 0.3, and the sigma 2 square is 0.5. And then we can calculate what the probability of choosing the alternative 1. So first of all, we need to calculate what's the value of sigma. Sigma is the square root of sigma 1 square plus sigma 2 square minus 2 times sigma 1, 2. With that, we get the value as 0.8037. That's the sigma. We also know the value of the v1 minus v2. With that, we can get the value inside in this cumulative function as minus 1.19. So as you have already get the value, then it will be very easy for you to find out the probability. And another thing we should know that for these two, the in general case we don't know. We need to calibrate. We need to use the observed variables attributes to calculate them. But for this example, we just assume that it's a no to simplify the explanation. And now for the for this cumulative function, cumulative normal distribution function, with the value of minus 1.19, you can get the probability from minus 1.19, which will give you the result as this one. Try to make sure that's. So as this result as this cell, that will give you the probability of 0.117. So the probability of choosing the alternative 1 is 0.117. And also you can apply the same method to find out the probability of choosing the alternative 2. So that's a very brief introduction about the probability model. But what if we have more alternatives? Not only we have more than 2 options for us to select. How can we extend the probability model to multinomial situations? So to do that, we will need to recall the Clark's approximation. This is one approximation to identify the maximum value of 2 random variables, 2 bivariate random variables. So assuming that we have 2 random variable, omega 1 and omega 2, they are multivariate normal distributed random variable. We know their mean and covariance. Those would be the general case. Their means M1 and M2, covariance is sigma 1 square, sigma 1 2, and sigma 2 square. And then we can find out the maximum of these 2 variables. The maximum of omega 1 and omega 2, I say that is omega 2 tilde. If omega 2 tilde is the maximum of these 2 variables, then it's also in the normal distribution. And with that, we assume that we can get the M2 tilde as the mean of the omega 2 tilde, M2 double tilde as the second absolute moment of omega 2 tilde, and sigma 2 square as the variance. So we can get with the Clark's approximation, for the omega 2 tilde, we have the mean as M2 plus M1 minus M2 times phi alpha plus A times little phi alpha. So here it's still be phi alpha, sorry. It's still be phi alpha. So M2 tilde is determined by this equation. And also we can get the sigma 2 square as M2 double tilde minus M2 tilde square. And here A is sigma 1 square plus sigma 2 square minus 2 times sigma 1 2 square root. And alpha is minus M1 minus M2 divided by A. So basically, if you know the mean and the variance of omega 1 and omega 2, you can find out the distribution of omega 2 tilde as the maximum value of omega 1 and omega 2. So that's the Clark's approximation. So we can also extend this approximation for the 3 alternative case. So for example, we consider the specific example. See, there will be 3 alternatives in the selection set, and we say that the UK is higher than, or the alternative case is selected, then the probability of choosing the alternative case, like the utility of the K, is higher than the maximum value of the other 2 alternatives. So in this case, if we do some slightly modification, that will be the maximum of the uj minus uk smaller than 0. With that, we can get another conversion, assuming that zj equal to uj minus uk, which assume that is omega j minus omega k, because the uj follows a normal distribution, and j will be if j is smaller than k, then j is k. If j is higher than k, j is j plus 1. So this is a slightly modification about the index to make sure that it's consistent with the other formula, the expressions of the normal distribution. And with that, we have this the probability of k is the maximization of Zj smaller than 0. And now if we are considering choosing the k, if we say that k equal to 1, then that will be the z will be u2 minus u1 and u3 minus u1. And in this case, that will be the maximization of z1 and z2 are all will be smaller than 0. And now we need to find out what's the distribution of z1 and z2. For the initially we assume, so here let's consider an example. Start with an example to do the analysis. So assume that v is we know the value of v is a 2, 2, 3. We also can get the we also have the covariance matrix for the random variable, and with that we can build the relationship between z and the z and the random variable, 3 random variable, which will be u times matrix delta. Say it's matrix delta. Z will actually equal to mu times the delta. Delta would be -1, -1, 1, 0, 0, 1. With that, we can find out the we can then find out the distributions of the z. So distribution for the deterministic component. For deterministic component, it's estimated based on the deterministic matrix, deterministic utility times the transform matrix, which is delta, as we derived previously. So we get a z bar as 0, 1, and we also need to find out what's the covariance matrix. So for the as z is the transformation from the it's transformation from the random components. So the the covariance will be the transformation matrix delta prime times the covariance matrix times delta, which will give you the result as 4223. So this would be the covariance for the z, and this is the mean value of z. With that, we know that z is a bivariate normal distribution with the mean of 0, 1 and the covariance matrix of 4223. And from Clark's approximation, we can find out the maximum value of z1 and z2 by using this list of the equation. To get that, we m1 equal to 0, m2 is 1, sigma 1 squared is 4, sigma 1, 2 is 2, and sigma 2 squared is 3. So we can calculate the value of m alpha. A is 1.732. Alpha is minus 0.577, and we can then calculate the value of the m2 tilde. It's and the value of the m2 double tilde from the distribution, for the normal distribution, we can get the value of the phi alpha. As little phi alpha is the normal distribution, the value is 0.337, and that one gives you the value as gives you the value of the of m2 and m3. So what do we get for m2 tilde? It's 1.302, and m2 double tilde is 4.5. And similarly, you can get the variance sigma 2 tilde as 1.7. And now, as you already have m2, you have m2 tilde and sigma 2, you can easily get the value of the probability. So the maximization of Z1 and Z2 follows a normal distribution with a mean of 1.3 and a variance of 1.7. The maximum value of this one is less than the maximization of Z1 and Z2 is smaller than 0. So with that, you get the probability of 1 is 5 minus 0.7659. And if we go to check the lookup table for the probability, the cumulative function of the normal distribution, the result would be around would be 0.2216. That would be the probability of choosing the alternative one. So that's how we're gonna apply the Clark's approximation to get the to find out the probability of choosing one alternative with three different options. And we will also be able to the Clark's approximation can also be extended to more than three alternatives or more than three variables. And here, let me show you how to do this kind of extension. First, let's start with two random variables, assuming that omega 1 and omega 2 are two multivariate normal distributed random variable. We know their mean and the covariance. And we know that the if we set omega 2 tilde is the maximization of omega 1 and omega 2, we can find out that it's also in a normal distribution. We can calculate their mean and variance. This is what we just explained. But if we have three variables, they also follows the multivariate normal distribution. We know their mean, we know their covariance matrix. Then we can find out the maximization of these three variables. First, we work on the maximization of the two variable omega 1 and omega 2 as omega 2 tilde. So we can, in the previous page, we can find out the value of the mean and variance. And this would be the equation we're going to use. We will also we claim that omega 2 tilde follows the normal distribution. And then we can claim that omega 2 tilde and sigma 2 omega 3 is also in the bivariate normal distribution with the mean of m2 tilde and m3. M3 is the one we defined. M2 tilde is the one we estimated from the previous step. And we also can get their covariance matrix as sigma 2 tilde square. This is the one we calculated in the previous page. For sigma 2 3 tilde, it's something we have to recalculate. Sigma 2 3 tilde will equal to sigma 2 3 plus sigma 1 3 minus sigma 2 3 times phi alpha 2. And alpha 2 equal to m1 minus m2 divided by a2, and a2 is determined by this equation. So we claim that omega 2 tilde and omega 3 is a bivariate normally distributed random variable. And then we can try to find out the we can apply if we want to find out what's the maximum value of these two, we can apply the Clark's approximation to find out the distribution. And this one can be extended to 4 variables. Say that for the four variables omega 1, omega 2, omega 3, and omega 4, there are 4 multivariate normally distributed random variable. We know their mean value, their covariance matrix. Then we can try to find out what's the distribution of the what's the distribution of the maximum value for these 4 variables. So we first assuming that there's a variable omega 3 tilde is the maximum of omega 1, omega 2, and omega 3. And this one can be modified as the maximum of omega 1. So we will first find out the maximum omega 1 and omega 2. This is just what we get, omega 2 tilde. As omega 2 tilde and omega 3 is in a bivariate normal distribution, we can find out the distribution of omega 3 tilde. And we also see that omega 3 tilde and omega 4 is in a bivariate normal distribution. And their means omega 3 tilde and M3 tilde and M4, and we can find out the covariance matrix where the M2 M3 tilde is determined by this equation, and omega sigma 3 square is determined by this one, and sigma 3 4 tilde is determined by this equation. Where we also need to use the 2 variables alpha 3 and A3 to calculate these variables M3 sigma 3 square and the sigma 3 4. So that's the that's what it extends for the 4 variables. With that, we can also have a very general situation. If we have n variables, they follow the multivariate normal distribution, and we know their mean and the covariance matrix. What we can do is, like, we can first find out distribution of the for the maximum of 2 variables, omega 1, omega 2, and then find out the omega 3 tilde and omega 4 tilde, omega 5, omega 6, until you get to the last one. It's omega m-1 tilde and omega n. So with that, you can get the distribution of for the maximum value of n variables. And once you know the distribution for this maximization problem, you will be able to find out the probability of choosing any one alternatives in the selection set. So that will be the generalization of the of this method. And in this calculation, we have listed the equations for you to calculate the mean and the variance for the maximum value in the next iteration, which is quite similar to the equations we proposed previously, similar to the two variable C scenario. And once you have the distributions, you have the you find out the covariance, you find out the mean values, you will be able to do the calculation to find out the maximum find out the probability of choosing any alternatives. So what we do is, like, for this kind of probability calculation, you will need to find out the transformation matrix. Say that if we want to find out the probability of the alternative K, all the utilities, you need to find out maximization of uj minus uk for all the alternatives. And with this one, you can determine the what's the transformation matrix. And the as we know the distributions of the z for the the distributions of the maximization about the z matrix we will be able to find out what's the probability from this from the Clark's approximation. So the for this part, as I say that it's not necessary for you to manage all of them. So I will just give you the quick check about the results. So basically, once you have the J different alternatives, you can get the distribution of Z. The maximization of that one follows the normal distribution with the mean of Mj minus 1 and the variance of the sigma j minus 1. And those can be calculated from the Clark's approximation, from the iterations from the first variable to the last one, from the first two random variable to the last to include all the variables in the maximization. And with that, the probability would just be the phi with phi minus mj minus 1 divided by sigma j minus 1. So this is the probability you need to recall to calculate the to choose the alternative k. And that's the conclusion, the simple conclusion from the probability model. As I say that you don't need to, in the previous pages I've showed the steps, so it's actually, you don't need to know how the whole solution, how the conclusion is derived. For the probability model, you just need to get this, remember this equation to calculate the probability. And but regarding to the values, mj and sigma j, you need to know how to do these iterations to get the result. So that would be all. I don't have enough time to finish the rest part about the calibration of the probability model. I will save this one for the next lecture. It will take like approximately 15-20 minutes to cover the calibration method. With that, I will stop here today. And do you have any questions about the probability model? Do you have any concerns? For the basically for the with all these two lectures, the lecture 9 and lecture 10, you will have all the necessary knowledges to work on the homework assignments and the projects. So just feel free to let me know if there's anything that is not clear to you. Or either send me email or during the office hour. I'm going to help you to understand the concept and the procedure to conduct the discrete choice model calibration with the logical models and the probability models. Okay. Okay. If there's any other questions, I think I'm gonna stop here, and just feel free to contact me if you want to know anything related to the to this class. Okay. I guess that'll be all today. And I will see you next week to finish the all the topics and start our introductions of the Queen's OD tutorial. Okay.
Thank you so much. Thank you so much.
Okay, that's great. Okay, good. And enjoy your week, and I will see you next week.
Bye.